100 years ago, the thought of going to space seemed far off and extraordinarily difficult. It was difficult and still is, but just as John F. Kennedy stated about landing on the moon, we do not do these things because they're easy, but because they're hard. I'm Lily Crolius, your host for Finding Beyond. Join me as we wake from our slumber, open our eyes, and venture forth to the vast skies above us. Getting to other planets and systems is an exciting task, but first we must get off the ground. Powering a spacecraft takes a tremendous amount of fuel. For example, each of the 2 rocket boosters on the space shuttle carries 1 million pounds of propellant. This fuel is composed of liquid oxygen and liquid hydrogen, which are mixed together to form a reaction that power the engines. However, even this is not enough to push the craft out of the Earth's orbit. Saturn V, the rocket used to launch Neil Armstrong and Buzz Aldrin during their Apollo 11 mission, had about 7.5 million pounds of thrust during takeoff, setting them at a speed of 7 miles per second. Voyager 1 flies through space at 11 miles per second, but even with this overwhelming speed, it took 36 years to exit our solar system and go radio silent into the night. In order to get humans to neighboring planets and systems quickly and efficiently, we must look at our quickest options for energy. One possible solution is nuclear energy. This type of energy is extremely powerful. For example, in 2017, the United States generated roughly 805 billion kilowatt hours of nuclear power. This is equivalent to 92 billion watts, or 1.5 billion LED light bulbs. Now, there are reasonable reservations that come from its other uses, like atomic bombs. One of the many feats of our society moving forward is not to use nuclear power for bad, but for good. Luckily, places like the Idaho National Laboratory have been doing just that. Their facilities cover a wide range of research topics, from homeland security to environmental sustainability, but the most useful to space exploration comes from their Space, Nuclear Power, and Isotope Technology program and its director, Dr. Stephen Johnson. INL is not only a leader for this area of research, but has powered about 27 NASA missions with nuclear propulsion energy, including both Voyager 1 and 2, the Mars rovers, and New Horizons, which will enter the outer ring of our solar system, the Kuiper Belt, in late December of this year. Having nuclear energy on board these crafts is important because things like dust storms on Mars and traveling further and further away from the sun render solar panels useless. On top of this, nuclear-powered crafts can go up to about 40,000 miles per hour, and the uranium-238 that power them have a half-life of approximately 4.5 billion years. But what is uranium-238 and what is a half-life? First, we must understand what an isotope is. An isotope is an atom that shares the same chemical properties as other elements, but has a different number of neutrons, giving it a different mass. And as you can gather from the name, radioisotopes are isotopes that are, well, radioactive.
Not everyone knows that many elements can have more than one isotope, which means they have the same number of protons in the nucleus, but a different number of neutrons. And some of these isotopes are not stable, so they will only stay around for a short period of time, or it can be tens of years, hundreds of years, but they're not stable.
Uranium-238 is a radioisotope that can be converted into plutonium-239 to produce nuclear fuel. The half-life of these are impressive, but why do we use the term half-life to describe how long something stays radioactive? Why not use the term full life? To put it simply, a half-life is not a measure of how long it takes to decay, but how quickly. I'm going to try and walk closer and closer to the whiteboard, but I'm going to go half the distance every time. Here's one half, here's one half of that, one half of that, another half, another half, another half. You see, I keep getting closer and closer to the board, but I will never fully reach it. This is something we like to call an asymptote. Now, the difference between a true asymptote and radioisotopes is that radioisotopes will reach zero, but it cannot be consistently calculated. When a radioisotope decays, it does not decay uniformly. Some atoms will go right away, while others may take countless years. The best way to estimate when something will no longer hold radioactive energy is to find the halfway mark, which is significantly more accurate than trying to calculate the end. Now, imagine with me for a moment this amazing atomic power, or whatever amazing and new power we are able to harness in the future, gets us to Mars or far-off planets. What will we do for energy? How will we sustain a colony and future society?
Why don't we talk about the possibilities of NASA transporting people to another planet like Mars. I think the technology to do that, to get them there safely, sustain them while they're there, have power systems on the planet, have a way to grow crops and so forth, is probably about 20 years out. The number that people usually use for a sustainable amount of power for a very small outpost, typically something around 35 kilowatts electric. And that would be something that you would want a small space reactor, a nuclear reactor. And that's something that I think you're likely to see demonstrated maybe on a lunar mission first, as far as just a technology checkout before you go all the way to Mars.
Theoretically, we could use whatever energy we had left on the flight to our new home, but that would not get us very far because nuclear energy is not renewable, given that it has a lifespan and the elements are well mined from the Earth. However, wind and solar energy are renewable. We see windmills scattered about and solar panels on top our neighbors' houses, but these forms of harnessing energy are vital for survival on an alien planet. Wind turbines will provide very useful on planets such as Mars that have a windy environment. The process behind these machines is pretty simple. The 328-foot-tall turbine is placed in an area with sufficient winds, like the Great Plains and even out at sea. The wind turns the blades, which are connected to a rotor, which in turn spins a generator to create electricity. Solar panels are a tad more complex, but are vital on planets that have a bright enough sun. If the panels are photovoltaic cells, which allow particles of light to separate electrons from atoms and cause electricity. Having a clean and renewable source of energy is also a way to heal our sick planet from all the toxins we are putting out. The Earth will eventually die. This could be from our sun expanding during its death and swallowing the whole world, an asteroid that just so happened to find the perfect target, or even a gamma ray from a far-off star. We cannot save the planet from this violent life cycle of the universe, but we can save it from ourselves. Even beyond this, we need energy to survive. We rely on it for food, warmth, light, transportation, and much more. Not only will this be a great way to start off on a new and healthy world, but also to save our home and origin, Earth. Join us next time on Finding Beyond.